Welcome to our penultimate episode, which is representing data run length encoding, part of compression. Today, hopefully you're going to be able to explain how to compress data using RLE or run length encoding, be able to represent data in RLE, and that's as far as we're going to get, because the second part of this lesson will be all about Huffman, which requires a separate lesson because it can be tricky for some people. There's a challenge down there if you want to pause it and have a look at that, and a number of keywords that hopefully be able to define by the end of these two lessons. Well, this one anyway, let's go on to this one, run length encoding. Very useful when data repeats itself often. So even though the example here is text, it's normally not the best for text. Normally for images is a good one. You might have big white spaces in your image, so it's good for run length encoding to say, oh, this whole row is white. Oh, and this next row is all white except for two pieces of black pixels. And this next row is half black, half white. And how you describe that can save you space. The example here is text. What you've got here is you've got 8 A's. 1, 2, 3, 4, 5, 6, 7, 8. Followed by 6 B's. 1, 2, 3, 4, 5, 6. Followed by 2 C's. 1, 2. And how run length encoding is it uses the value followed by the frequency, or the other way around, the frequency followed by the value. In this one, we're doing value frequency, so the value is A, and there are 8 of those A's, and we count, there's 8 A's, followed by the value B, which and there's 6 of those, and there's 6 of those, followed by the value C, and there's 2 of those. And that's run length encoding. Or you could have done it the other way. You could say you could have done frequency value, so you could have said there's 8 A's, followed by 6 B's, followed by 2 C's. It doesn't really matter which way you put it. Now, even though the example here is text, text is not a good use of run length encoding, because if you think, just let's take this text on this slide, where are there repeating letters? Double O's, double T's. You know what? I'm quickly scanning this. Double M right there. Double T. Now I quickly went through that, but I didn't see much, so that's not really good. So everything would have said there's 1 R followed by 1 U followed by 1 N followed by 1 hyphen followed by 1 L followed by blah 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 until eventually 1 I followed by 2 M's. You're not going to save much space doing it that way, so it's not very good normally for text. But let's look at some text examples just because it keeps it simple. Here we're going to compress this string AA, AAA, BBB, CC, CC, DDE. Let's do it by doing frequency followed by value. How many times does A occur? 1, 2, 3, 4, 5 times. So there are 5 A's followed by 3 B's followed by 4 C's followed by 2 D's followed by 1 E. And there you go, look. There's your frequency, 5, followed by the value, A, and so on. 5 A's. If we needed to recreate that, we could just write it back out again. 5 A's, followed by 3 B's, followed by 4 C's, followed by 2 D's, followed by 1 E. Cast your mind back to how we store uncompressed data in ASCII. Every character is 7 bits. So looking at the string up here, there are 15 characters. So that's 15 times 7 would be 105 bits used. But when we use run length encoding, we brought it down to these number of characters. Each of these characters, and look at this, A, B, C, D, and E, there's 5 of those, that's 5 times 7, that's 35 bits. And then we'd have to record the binary for each of these. So what's binary for 5? 101, so that's 3 bits. What's binary for 3? 11. What's binary for 4? 100. What's binary for 2? 10. And what's binary for 1? 1. So looking down here, 3 plus 2. These are the number of bits, by the way. 3 bits to represent 5. 2 for 3, so that's 5, 8, 10, 11. So that's 11 bits. So 5 characters are each 7 bits. 1, A, B, C, D, and E. That's 35 bits. And then in binary, what would you need to represent each of those numbers in binary and add up the number of bits it takes you to do that, which is 11. So there's 46 bits. So if you think you had 105 before and now you've got it down to 46, you've saved an awful lot of space. Best way to learn those is for you to try. There's a string there. Compress that to run length encoding. Work out what size that would be using run length encoding. And then tell me, why is that a bad idea then to use for run length encoding? Pause the video, have a go. Well, welcome back. What would the run length encoding string look like? Well, there's 1A, followed by 1B, followed by 1C, followed by 1D, followed by 1E, followed by 1A, followed by 1B, blah, 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 blah. Gets you all of this. So what size would it be for run length encoding? Well, there are 15 characters there, so that's 15 times 7. So that's going to be 105 bits for that, because of the A, B, C, so 1, 2, 3, 4, 5, that's 15 of those. Then to store 1 in binary, you need 1 bit, and there's 15 of those. 1, 2, 3, 4, 5, 6, 7, up to 15. So 105 plus 15 is 120. So it would take you 120 bits to store that in run length encoding. Why is that a bad idea? Well, if we hadn't even bothered compressing it at all and just used 7 bits for each one of these letters, that would have been 15 times 7, which is 105. So actually, if we didn't even bother compressing it, it would have been a smaller file. That's why it's a bad idea. That's why it's normally not used on text. It's much better for images, though that will depend on the image itself. So nice black and white images, perfect run length encoding, but a photo of, say, a complex scene with a number of people in it wearing different coloured dresses, not going to be great either. There's other compression techniques you can use for that. So anything with the black and white images normally got a long run of pixels that are of the same colour. Not always. Well, again, it depends on the image, but generally speaking, a black and white image is going to have more than one of the same colour, unless it's like a grid or like a chessboard or something, but normally it won't be. There'll be lines which will be all the same colour. Let's show you a black and white image of like a Space Invader type character and how that would look in run length encoding. We're going to use frequency followed by value. So this is a 10 by 10 grid. First row, if we represent these zeros as whites, there are 10 whites, 10 zeros, so it's 10 0, followed by 2 zeros, and then black is represented by 1 and 1 1, followed by 4 zeros, and then 1 1, and then 2 zeros, and so on. And that's how you depict each of these. Now in this example, we've used black and white, and we're using it as frequency followed by value, and the color depth here is 1, so we're only using 1 bit, so a 0 or a 1. If the color depth had been 2, we'd have to represent it as 0 0 or 0 1 or 1 0 or 1 1. So you might say 10 followed by 0 0, 2 followed by 0 1, that kind of idea. Get yourself off to Edmodo, go and have the quiz called Representing Data Run Length Encoding. Once you've done that, the recap, run length encoding, you should hopefully now be able to explain how we do that to compress things. You should be able to represent data yourself in run length encoding using frequency data pairs or data frequency pairs. And that's about as far as you'll get for this lesson, because the next 2 success criteria is our next lesson on Huffman coding.